Alright, I have you two waves with different frequencies and different amplitudes. When I superpose them, this is the wave you are going to get. This is sine of t with amplitude 1 and frequency 1. That's sine of 3t with amplitude 1/3 and frequency 3. When I add them, this is the function you get. This wave, this is y1 of t, y2 of t, if you call this direction t, then capital Y of t, the superposed wave, is the combination of y1 and y2. And so how do you add them? Well, you add functions values at the same moment in t's. So these are the same moments in t. So you take this value of the function and you add it with this one, you will end up somewhere here. And you can do the same here now. You take this value of the function, looks like it's negative because it's below horizontal line, add it with this one, you get down somewhere here. And now you can do it for all the points now along the way, and then you connect all of those points and you construct this wave out of the combination of these two functions. And I can make you hear that with the guitar. I have 6 strings with different frequencies. This is a 330 Hz, next to it 250 Hz, and the last one 80 Hz. So for now, pretend these are the traveling waves that you're going to hear. Of course, I have to modify these equations to have spatial and timing information for them to behave like a traveling wave. On the guitar, they are standing waves. In air, they are traveling waves. So suppose you have 6 waves with different frequencies and different amplitudes. Of course, I can manage the amplitudes with my fingers because that's what I'm going to do. And now, I will make you hear them one by one. This is what 2, 3, 30 Hz sounds like. Now 250 Hz. Now lower, lower, even lower, and the lowest. You heard them individually. Now I'm going to strike them, excite them at the same moment in time, and what are you going to see? What are you going to hear? Not see. This kind of pattern, this kind of wave, a little bit more complicated, but that's the idea. And if you are ready, then, and indeed that's a different sound because it's a superposed sound. And this is the idea of Fourier series. I can construct you any periodic function as the combination of sines and cosines. Maybe I want to make you a triangular wave, periodic wave. Maybe I want to make you a square wave, like this. And notice this triangle repeats itself after a period, maybe t. And this one, this square wave, repeats itself. This pattern goes on. It also goes backward and moves forward, and it has a period t. And so any function that keeps on repeating itself, its pattern, after a fixed period, we call them periodic function. And so that's what we are looking for. So I have a function f of x, and it's the periodic function. That is going to repeat itself after 2 pi period. And I want to write it as the combination of cosines and sines. cosine of nx, sine of nx, and I want to have many of these different cosines, many of these different sines. So I run a summation, and I want each of those cosines to have different amplitudes, and I want the same for sines. So here you have cosine waves, many of sine waves, many of cosine waves with different amplitudes, and different frequencies. So if you have here cosine of 7x, then a7 would tell you what fraction of that cosine wave will end up in the function. If you have here sine of 5x, then b5 is going to tell you how much of that sine function will contribute in making the main function. This sum goes from 0 to infinity, and this goes from 1 to infinity. We don't have to have a 0 here, we don't have to start with 0, because when I put n equals 0, sine of 0 is 1, and so we do not need b0 in the sum. But you are going to see a a0, because when I put n equals 0, cosine of 0 is 1, and so you're going to have a a0 in this infinite sum. And now I'm going to write this summation in its full form. When I put n equals 0, put 0 here and 0 here, you get a0, and now put 1 here and 1 here, you get a1 times cosine of x. When you put n equals 2, you get a2 times cosine of 2x, and then it moves forward. Here you will have cosine of 3x, 4x, 5x, moves forward, and then somewhere here in between you're going to have a term ak times cosine of kx, and k could be anything, it could be 11, 15, whatever. And now I will write this. This is going to start with b1 times sine of x plus b2 times sine of 2x, and then it moves forward, keeps on going forever. And so this is our infinite sum of cosine and sine waves. And what we are looking for, what we have to find, these coefficients, these amplitudes, ANs and BNs. So we have to find A1, A2, A15, B1, B15, B40, whatever, because they are going to tell you whether a wave is going to contribute into the function, into the main function. Maybe if a2 turns out to be 0, then it would tell you cosine of 2x, we do not need it. We do not need it into the function. And maybe if b2 turns out to be half, then it tells you you have to take the half of sine to x wave. And what I mean by taking the half, that you do not cut your wave into two parts. No, that's not what I mean. No, I mean you take your sine of 2x and you squeeze it down by a factor of half. That's what I mean. And so how to find these ANs and BNs? That's the question. And the answer is orthogonality. This is the Fourier trick. And what I mean by orthogonality, if I take a cosine wave, cosine of nx, and I multiply it with a different cosine, cosine of kx, and I integrate it over that period 2 pi, from minus pi to pi, this could give you either 0 or pi. It depends. If n is not k, it gives you 0. If n is 5, k is 7, gives you 0. If n is 11, k is 15, again gives you 0. And so we say these cosine waves are orthogonal to each other. That's what it means by orthogonality. It gives you 0 when you integrate them. But it gives you pi if n is k. If this is 11, that is 11, we get pi. If this is 5, this is 5. Again, we get pi. And this integral is going to help us. That's the key. That is going to find us those amplitudes, those coefficients. And what I'm going to do now is, I'm going to take my function and I multiply it both sides with cosine of kx, and I integrate it from minus pi to pi. So I take my function f of x, I multiply it with cosine of kx, integrate it from minus pi to pi. So I take this term, this summation, minus pi to pi, the summation over sine waves, an times cosine of nx plus, now this one, summation over sine waves, sine of nx, and now I have to multiply with cosine of kx dx. And this is the idea. That's the big idea. This is going to help us. So it's like integrating this from minus pi to pi times cosine of kx dx. And now follow me closely, because many things are going to disappear. When I take my cosine of kx dx with the integral sign and I distribute it inside, it comes here and there. So it's like multiplying each term inside everywhere with the integral sign. So you have here individual integrals, infinite number of integrals. And when I take cosine x times that partner function, cosine of kx, and I integrate it from minus pi to pi, look, I get 0. And when I take cosine of 2x times cosine of kx, again gives me 0. So all of these sine waves, cosine waves that you have here, with that partner function, all integrate to 0. Even the first term is going to give you 0. When this cosine of kx comes down here, it is without the partner. Well, still it gives you 0. When you take any cosine kx, any cosine wave, and you integrate it from minus pi to pi, still gives you 0. And so let me write it. You take any cosine wave and you integrate it from minus pi to pi, gives you 0. And it holds for sine waves too. So you can take any sine wave, still gives you 0 when you integrate them from minus pi to pi. Even those, when you integrate sine nx times cosine kx, even they give you 0, because all the sines are orthogonal to all the cosines. And so all of these integrals with that partner function, cosine of kx, all of them will integrate to 0. So who survives? Well, only one term survives when n is k, because somewhere here you're going to have a term ak times cosine of kx, and then when you multiply it with that function, you get this, because now n is k, and k could be 47, and somewhere here you're going to have a term a47 cosine of 47. So that's the one that survived. That's the survivor. And all of those integrals in this infinite sum, all of them disappears. Only one survives. And that is the integral from minus pi to pi, ak cosine squared kx, right? Because n becomes k, so this becomes cosine squared kx dx. And this is a very easy integral. This has This becomes ak times pi. And look, I have found you kth coefficient for those cosine waves. And so all I have to do is, because this is that, all I have to do is I have to divide it by pi. So let me remove it. So ak becomes 1 over pi, this integral from minus pi to pi of that function cosine of kx dx. And in the same way, you can find bk. It is going to be exactly the same, 1 over pi integrate from minus pi to pi of that function with one change. Now this is here sine of kx instead of cosine of kx dx. And how do you find that bk? Well, instead of multiplying with cosine of kx here, you multiply with sine of kx. And this holds for sine waves too. So if you have sine of nx times sine of kx, you get 0 when n is not k, and you get pi when n is k. So in the same way, you can also find bk. But there's a different formula for b a0, and that's what we have to find. You cannot find a0 from here. No, we have a slightly different formula. And so remember, when I was multiplying this function f of x, this is f of x, this was coming right here, and when I integrate this single cosine kx wave, it was giving me 0. And so it sort of suggests me that I remove cosine kx and I just integrate this function. Just integrate it without cosine of kx. Because now, when you're going to distribute integrals inside, these cosines are left alone. They are left, left alone. And these are left alone. And so when you integrate a single cosine wave, any cosine wave is fine. You can pick any sine wave as you please. All of them are going to disappear. All of them will give you 0. And who is going to survive? Well, a0 is going to survive. So let me remove some of that, because I'm not going to need space. So who survives? a0 survives. And this integral was from minus pi to pi dx. And this is a very easy integral. That's a0 times 2 pi. And this was the function that we were integrating without multiplying cosine kx, right? And so you have found a0. All you have to divide this by 2 pi. So a0 is going to be 1 over 2 pi from minus pi to pi of that function, or dx. And these were the amplitudes we were looking for. There you have it, a0, ak, bk. They tell you whether a particular wave is going to contribute into the function in making the mean function. And I want to show you now why these crazy integrals were giving you 0, why they give you pi, and why those single waves, when you integrate them from minus pi to pi, why were they giving you 0. And I will show you this on my computer screen. This is sine of 2x, that's sine of 3x. When I multiply them, this is the function you are going to get. And when I integrate it from minus pi to pi, I will look for the areas under the curve. Well, that's what integrating a function tells you to do. Look for the areas under the curve. Alright then, notice this area is exactly the same as this one, except this has the negative sign because it's below this horizontal line. So they cancel each other. Together, they give you 0. And notice the same thing is happening here. This area is exactly the same as this one, but this has the negative sign. And if you integrate it from here to there, you get 0. And you can see for beyond the wall, I call this wall, the same thing happens on the other side of that wall. So the area from minus pi to pi is 0. It tells you the integral over that minus pi to pi is 0. And this happens when n is not k. And now I can show you this for cosine waves. Cosine of x times cosine of 4x, that's the product of these two functions. And you can already tell because the integral from minus pi to pi is going to be 0. You can see that because you have to look for the areas. Look at this and this one, exactly the same but with the opposite sign. And look at them, and look at these two, the little ones. All of them give you 0. And so this integral from minus pi to pi is not going to survive. And when I take sine wave and cosine wave, and this is sine of x times cosine of 3x, and you can tell for yourself, even this integral is not going to survive. It's very easy now, right? Remember, I told you, even when you take a single sine wave, any sine wave is fine, you can take any one, or you can take any cosine wave, in this case it is cosine of 3x, and if you integrate them individually from minus pi to pi, both of them will give you 0. Because look at this area and this one. They have the opposite sign, but they are equal, give you 0. And the same goes for cosine of 3x. Now I will talk about survivors. This is going to survive. Cosine squared x is going to survive because you are no longer going to see any negative areas, any areas with the negative sign, because this curve is not going to fall below this horizontal line. And now this area, all of that under this curve has a value, and I have given you that already. I have told you it is pi, and so this is going to survive because it is a survivor. So cosine squared x survives, cosine squared 2x survives, and still the area under the curve is pi. Cosine squared 3x survives, and the same goes for sine squared x survives, and still this area under the curve, again pi. Sine squared 2x survives, sine squared maybe like 100x survives, sine squared 1000x survives. So all of these are survivors when n is k, when n equals k. They survive, all of them. And absolutely crazy that the area under these three curves share the same value, and this is pi. Area under this curve and this one and that one, all of them, and the integral is pi. And you cannot tell just by looking at them. It's really non-intuitive that they are going to end up with the same value of area, same value for the integral, that's pi. absolutely non-intuitive. And I wasn't showing you any higher harmonics because when I take sine of 7x, sine cosine of 12x, and when I multiply them, look what you get. You get like a complete zoo